As you know, energy is a big part of our course. We're talking about interactions here that are based on charges, or at least partial charges. We remember from Coulomb's law that interacting charges have a potential energy associated with them. So let's compare the energy of the three states of matter and how the energy might change with the strength of intermolecular forces. We have a one-dimensional plot where interaction energy is on the y-axis. We know that in an ideal gas there is no interaction between the molecules, so the interaction energy of an ideal gas would be zero. The first question to consider is this. If we were to locate the energy of a real gas on the plot, would it be at positive energy or negative energy? To answer that question, think about the three intermolecular forces. Dispersion is the attraction of opposite charges from temporary dipoles. Dipolar forces are the attraction of opposite charges from permanent dipoles. Hydrogen bonding is the attraction of a partial positive hydrogen to a lone pair of electrons. They all arise from the attraction of opposite charges. Coulomb's law tells us that the potential energy of these interactions is negative. So we'll add the energy of a gas at negative energy. Next, we need to ask whether the strongest interaction occurs in the solid, liquid, or gas state. Once we decide that, then we can add the levels for the solid and liquid to the diagram. If we think in general about the three states, the molecules are farthest apart in the gas phase and closest together in the solid, where the plus-minus interaction is maximized. Coulomb's law tells us that opposite charges close together will have the strongest force of attraction, so the strongest interaction will be in the solid. Coulomb's law also tells us that opposite charges close together should be at more negative energy, or lower energy, than if they are farther apart. So we can add the levels for the liquid and solid at the lower energy than the gas. Let's ask one more question about this diagram. Suppose the picture we have is for a material with weak intermolecular forces. If we were to plot the levels for a material with strong intermolecular forces, where would they go? At higher energy or at lower energy? In terms of Coulomb's law, stronger forces is equivalent to having larger charges. When opposite charges get larger, the energy goes lower. So, in a material with weak forces, the energy gaps between the states are relatively small. So we'll redraw that. For the material with strong forces, each state will be lower than the corresponding state in the weak diagram. One result of this is that the energy gaps between the states are greater. This is consistent with what we have been saying about boiling points. In the material with weak forces, the amount of energy needed to go from liquid to gas is relatively small. You don't have to supply too much energy, so the temperature does not need to be raised all that much. The boiling point should be relatively low. In the material with strong forces, the energy gap between liquid and gas is larger, so you would need to supply more energy to make that jump. The temperature would need to be raised higher, and we would observe a higher boiling point.